I am Alper, and this is a joint work with you, Wang, Michael Zavlanos, and Pajic. Okay, so we are interested in learning a control policy from a given specification in an unknown environment. We model the environment as an MDP, where the transition probabilities and the topology are unknown. We use linear temporal logic to describe the desired task. It's just a simple extension of the propositional logic with some additional temporal modalities like next operator, until, eventually, and always. The satisfaction of the formulas here depends on the paths generated. So our problem here is to find a policy using reinforcement learning such that the probability of the paths generated by that policy that satisfy the specifications is maximized. Simply, we want to design a reinforcement learning framework which takes the specification and the model as inputs and produces a desired control policy. Okay, the first step is to use a standard model checking technique constructing a product MDP. Usually the automata constructed here need to be deterministic, but recently it is shown that if a limit deterministic BK automaton is constructed in a certain way, then we can say a policy that maximizes the probability of satisfying the BK objective in the product, and this induces the desired policy in the original MDP as well. Here's an example. So this is a simple LDBA. We are allowed to make a single non-deterministic transition, then we get stuck in this deterministic component. This is the MDP. Alpha, beta, and theta are actions. A and B are the labels of the states. When we construct a product MDP, we can see there will be some epsilon actions here. Epsilon 1, epsilon 2, here and here as well. So because of these epsilon actions, there is no one-to-one mapping between the paths. But that's okay. The theorem says if we map the best policy in the product MDP to the original MDP, we obtain the best policy we want here as well. For instance, taking beta and epsilon 2 and theta is the best policy on the product, and it induces choosing beta and theta, which satisfy the LTL specification here with probability of 1. All right. So what we propose in this work is an approach that transforms the acceptance condition of the product MDP into a reward function and a discounted function. So the capital B represents the set of accept states in the product MDP, the ones with double circles. So here's the idea. Whenever we visit an accept state, we receive a small reward encouraging visiting it many times. Let's say all the states on a path is an accept state, and they like sigma equals B, 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 then the total reward gained, which is return, on this path will be something like this. So if all the paths generated by a policy are like this, then we can say it satisfies the objective with a probability of 1. So we want the return to be 1, therefore we set R to be 1 minus gamma B here. But how about non-accept states? There will be some additional discount factors here to deal with this issue. So why don't we use a single discount factor? Let me try to illustrate this on this simple example product MDP. So there are two possible pure policies on this MDP. The one chooses up and the one chooses down. And if we do the math, we obtain these values. 0.9, and if gamma is something close to 1, this is something close to 0.5, which means the optimal policy actually favors up over down, which is something we don't want, because down surely satisfies the objective, on the other hand, up does not. The problem stems from the fact that we don't care the frequency of visiting a B state, as long as it's visited infinite many times. That's why we use two different discount factors to increase the importance of visiting these states. Okay, so the other issue, can we just ignore all non-B states by setting gamma to 1? So the problem is it creates a convergence problem in reinforcement learning. Here is is a slightly modified example. And our algorithm might overestimate the value of this down action during learning. If that happens, the estimate of this action, the value of this action, cannot be corrected due to the lack of discount. This happens when there are some end components in the product MDP. So we need discounting. Okay, so here's our theorem. For simplicity, let gamma be as a function of gamma. This is the value of state, which is the expected return from that state we can obtain. So if you use the reward and discounting function we have described, and if gamma b dominates gamma, then we can say as gamma goes to 1, the values approach the satisfaction probabilities. And since there are only finite many policies there, there always exists a sufficiently large gamma that gives us the best policy. Okay, so we applied our method on 2 different case studies. Both of them are based on a 2-dimensional grid example. So every cell in this grid represents a state. A, B, and C are the labels of states. This is an obstacle, and the encircled states are absorbing states, which means it's not possible to escape from these states. The agent can move in 4 directions, and there's a slight probability that it can go sideways. So we have a simple objective here, which is to reach a safe absorbing state and stay there without visiting a C state. So this is the corresponding LTL formula, and this is the control policy we obtained using reinforcement learning. The worst state to be here is actually to be in this state, because whatever action we take, we can end up in a C state. So that's why it tries to escape from that state. So here's a similar situation, and a similar situation here as well. And interestingly, the best policy here actually relies on noise to do the job. However, it's a safe policy and it satisfies the objective. And these are the estimated satisfaction probabilities. Okay, here's our second case study. This is a little bit more complicated scenario. It is the same grid world with different labels and objective. So A is for adult, C is charger, B is the baby, D is a danger zone. And the task here is repeatedly checking the baby and going back to the charger. In the adult must not be visited. However, if it hits fall in this state, it wakes the baby up, and if that happens, the adult must be notified. The objective is represented by this LTL formula, and these are the policies obtained using reinforcement learning. The most likely paths are highlighted in red. It goes from C to B and B to C without visiting A, but if it's the ball, it visits A and goes back to baby again. Okay. All right. In conclusion, we propose a framework to transform the control synthesis problem from LTL specification to an RL task. We do this by converting the objective into a reward maximization problem. We show that using the rewards and the discounting we described ensures the convergence of the RL to the best policy. The immediate future work would be to deal with the slow convergence rate faced here, which is the direct outcome using large discount factors. And the second future work might be handling cases with large state space where we cannot use tabular methods. We might need to use some approximate methods. Okay. Thank you.